on principle of work and energy, it says that the kinetic energy plus work done equals the final kinetic energy. So first question, the 10-pound sphere starts from rest at theta equals 0. So this is where it starts. This is instant 1, and rolls without slipping down a cylindrical surface. So rolls without slipping is key, which has a radius of 10 feet. Determine the speed of the sphere's center of mass. So we need to find the velocity of the center of mass, g, at the instant when theta is 45 degrees. Okay, so this is the second instant of time. So let's draw the free body diagram. Always a good idea to draw the free body diagram. I'm going to draw the free body diagram when the sphere is at a generic angle theta equals, well, theta is not equal to 0. So this is theta, this is the center, and the normal force is always going to pass through the center of the circle, right? So that's the normal force. It's mg. Is there any other force? There should be friction, right? Because it's rolling without slipping. Friction should prevent it from slipping, so there should be friction. Okay. Those are the three forces. Okay, so I need to solve for velocity at theta equals 45. So one approach is, and this is something which you've done in the previous, this is something which you covered in the exam, which is you can solve for, it's a rolling without slipping problem, you can solve for the angular acceleration and the linear acceleration of the sphere, right? Once you find the linear acceleration, you can integrate the linear acceleration to find the velocity. And that's how you can solve this problem. That's one way to solve this. However, as I told you, I keep repeating this, is when you're asked to find velocity as a function of displacement or distance or angle, v as a function of theta, you're better off using principle of work and energy. It just makes computation easy. Okay, so two ways to solve it. Find AG. So this is something we did in chapter 17, and then integrate to solve for VG. You can try this at home. I'm going to do this by principle of work energy, as V is asked as a function of theta. That's what we use. So let's find the energy. So when I say 1, it means that I need to find the kinetic energy at 1, I need to find the kinetic energy at 2, and then I need to find the work done going from 1 to 2. So what's the initial kinetic energy from rest? So it's 0. What's the final kinetic energy? So what's the energy expression for a rigid body which is rolling? I told you that this is general planar motion, so it has to be half mvg square plus half ig omega square, right? Okay, we do know, however, that Vg is, let's call this as capital R, and this the radius of the sphere as small r. So Vg is small r omega, because since the contact point is not slipping, this point, velocity is going to be simply omega times the radius. This is the radius. Okay. What is Ig? Do you know the inertia for a sphere? It's in that table. I think it is 2/5 mr square. 2 divided by 5 mr square. So we can now write T2 as half. I'm going to sub this in here to get mr square omega square plus half times 2/5 mr square omega square. So if you do the simplification on that, I think you should get 7 divided by 10 mr square omega square. Okay. And finally, the work done in going from 1 to 2. So when you find the work done, you need to ask yourself, what is the work done due to the individual forces acting on the system? So there are 3 forces. There is a friction force, there's a normal force, and mg. So what's the work done by the normal force? So it's going to be n times the displacement of this point in the direction which is normal at that instant of time, and there is no displacement in that direction. So the work done is 0, because the sphere is going to have acceleration only in the direction which is along the instantaneous tangent. It's not going to have an acceleration in the vertical direction. So the displacement in the vertical direction is going to be 0, which means that n dot displacement is going to be 0. The work done by friction force is going to be what? So again going to be 0, because that point which is in contact does not slip. So when the point doesn't slip, the displacement can be taken to be 0, and so the work done is 0. The only work done here is due to mg. Mg times the distance moved. So mg acts downwards, and the displacement let's call that delta y. That is also downwards. So mg times delta y. Okay. The sign on the work done is going to be negative or positive. It will be negative. Well, mg is downwards, delta y is downwards, so it has to be positive. Positive U12 is positive as mg is downwards, the displacement is downwards. So what is delta y? What's the distance moved by the center from here to here? What's this height? What's that height? What's that? Yeah, so it's r plus small r, right? And what's this height? It's going to be very similar. It's going to be r plus small r times cosine of theta, because this is theta. So delta y is going to be r plus r minus r plus r cosine theta. So we can write this as mg . r plus small r minus r plus small r cosine theta, which is mg capital R plus small r 1 minus cosine theta. Okay, so we all set to find the work done. So let's just write this down. T1 is 0 plus U12 is mg capital R plus small r 1 minus cosine theta, and then the T2 is 7/10 mr square omega square. So m go away, g is 32.2, r is capital R is 10, small r is 1.5. 1 minus cosine of 45 degrees equals 7/10 of r is 0.5 square, and omega square is the unknown. So if we solve for omega, you get I did not quite write that. I just wrote v, which is omega r, which is 11.9 feet per second. So omega has to be 23, right? 0.8. Because if you multiply with 0.5, you should get okay. So no need to integrate. The advantage of this method is if you are done with method 1, which I wrote down here briefly, you had to integrate. In this case, you do not have to integrate. That's the advantage. That's why it makes computation slightly easier. Any questions on this? Yeah, it's basically this, which is r plus r. We need to find the height in the vertical direction, so that's going to be r plus r cosine theta. So this is going to be this times cosine theta is going to be this, because we need to find the height of the center of the sphere. A common mistake here is people take it to be r cosine, capital R cosine theta, but that gives you this height. You want this height. So it's r plus r cosine theta. Because this is r plus r. Center of this circle, the center of that circle is small r plus capital R. Any other questions? Okay, let's go to the next question. The pendulum consists of a 10 kg uniform disc and a 3 kg uniform slender rod. So 10 kg disc, 3 kg rod. If it's released from rest in the position shown, so released in the horizontal position, determine the angular velocity when it rotates clockwise by 90 degrees. So this is going to be the final configuration, right? 90 degrees. So this is our instant 1, this is instant 2. We need to find the angular velocity when the angle turned is 90 degrees. Okay, let's draw the free body diagram first, and I'm going to draw it at a generic configuration, something like this. Okay, so when I release the pin joint, I would have a vertical force because there is no pin joint now, and I replace the effect of the pin joint with a reaction force due to the pin joint. There's a moment, it's constant, it's given like so. There is m, let's call this m2. So this is m2 and this is m1. Okay, so this is m2g, m1g is going to be somewhere here, and of course this angle is theta. well, rather, yeah, let me not specify an angle. I think the angle is measured from the horizontal, so this should be theta. If you like, well, you can write this as theta, because that's how it seems that that's how theta is measured for this particular problem. So theta is 0 is that configuration. Okay, so again, the key here is you have to find angular speed for a given angle, which means you need to find relation between speed and angle, or speed and theta, which means you're better off using principle of work energy. The other way to do is write F equals ma and integrate, solve for angular acceleration alpha and integrate that equation to get omega. But as I said, easier way is to use principle of work energy because of the thing which is asked, speed as a function of theta. So principle of work energy, which states that T1 plus U12 is T2. Okay, so T1 is going to be 0, the release from rest. T2, to find T2 we need to find the energy of the composite pendulum, which consists of a slender rod and the disk. Okay, and we need to find the inertia about A. So half inertia about A for rod omega square plus half IA for disk omega square, right? We need to find inertia about point A. Okay, so we do not know a formula for inertia about A. We do know the formula for inertia about G. For this, it's mr square divided by 2. It's ml square divided by 12 for that. So we're going to use that and parallel axis theorem to find T2. So half, this is going to be m1l squared divided by 12. That's the inertia about G. And then m1 times this distance. It's going to be L. So let's call this L. So L divided by 2. So m1 L1 divided by 2 square. Just L. Okay, then for the disk, the inertia about this point and axis passing through the plane of the paper, that way is mr squared divided by 2. So let's call this distance as small r, so m2 r squared divided by 2, plus we need to find the inertia of the disk about A. So we need to find the distance from A to the center of the disk, which is going to be this distance. That's L plus R. So m2 L plus R square. Missing omega square and omega square. Okay, and then finally the work done. Okay, so for the work done, again, look at the forces. There are 5 forces: H, VA, M, M1G, and M2G, out of which HA and VA do no work because point A does not move. Okay, the only contributions would be due to capital M. That would be the mass, the moment times the angle turned. So it's going to be pi by 2 minus 0. Okay. Now the question is, what's the sign on this? So M is clockwise, and the angle turned is clockwise. So when you have forces, remember when we talked about work done for a force, if the force and delta R is in the same direction, the work done is positive. When mg moves the mass down, it's positive work. When mg moves the mass up, it's negative work, because mg is downwards, displacement is upward. So the multiplication gives plus times negative is a negative. In this case, m is clockwise, so you can assume it to be negative because it's clockwise. But delta theta displacement is also clockwise. A convention is clockwise negative. So negative times negative for m times delta theta would give you a positive. This is positive. Then the work done to m1g is going to be m1g times the distance moved, right? So what's the distance moved? This is going to come over here. So the distance moved is going to be L by 2. And since M1G is downwards, L by 2 is downwards, the multiplication will give you a positive sign. And then there's M2G times the distance moved by the center, which is going to be L plus R. So L plus R. Again, M2G is downward, L plus R is downward, so the sign, when you take the product of those two, you get positive. Okay, so we all set to write this. So it turns out that I actually computed T2. As I put the numeric values for M1, R, small L and R, and I got 31.2 omega square. I also tried computing this by putting the value for M and other things, and I got 312. Okay, so now using principle of work energy, I can write 0 plus 312 is 31.2 omega square, and so it's trivial to get omega. It's square root 10, which is 3.16 radians per second. Okay. So again, as I said, in this specific problem, if you chose to use F equals ma, you will have to find acceleration of the rod, and then you need to integrate that acceleration to find the angular speed. However, by using the principle of work energy, you do not have to integrate any equation. So it's simpler. That is, if you don't like integration. The other thing is, why do we even draw a free body diagram? What's the purpose of drawing a free body diagram? Because I drew a free body diagram, I could reason out about U12. There are forces, and I need to find the work done due to those forces. When I have a clear free body diagram, I can figure out which of the forces contribute to the work done and which don't. So I highly recommend drawing a free body diagram, even if you're told not. If you're not asked to draw a free body diagram, please draw it, because that makes your life easy. So a common mistake which people might make in this particular problem is they might skip one of those M1G forces if they had not drawn the free body diagram. Okay. Any questions on this? So the 10 kg rod AB is pin connected at A and subjected to a couple moment M, 50 Newton meters. If the rod is released from rest, when the spring is unstretched at theta is 30 degrees, determine the rod's angular velocity when, so find the angular velocity when theta is 60 degrees. As the rod rotates, the spring always remains horizontal because of the roller support at C. Okay? So starts off at 30 degrees, and clearly it goes down because of gravity, not shown here. The rod or the spring moves only in the angle of the spring doesn't change, it remains horizontal. So it's, because the roller is going up and down like that, and then you're going to find the angular speed when the angle has changed to 60 degrees. Okay, so again, the key thing to note is that you're told to find the speed when the angle is 60 degrees. So omega as a function of theta. You're better off using principle of work energy. So let's draw the free body diagram and set up the work energy equation and go from there. So free body diagram. Okay, release the pin joint, which will be replaced by a vertical force and a horizontal force. Mg, due to the weight of the rod. There's a moment M, and of course there's a spring force, which will always be horizontal. I call that K delta X. Okay, is there any other force I'm missing? I think that's it. Okay, so principle of work energy. T1 plus U12 is T2. T1 is 0 because the rod is released from rest. T2 is the kinetic energy of the rod, so that's going to be half inertia about A omega square. So half the mass, the inertia about A is going to be ml square divided by 12. That's the inertia about G, which is this. And then I need to add to it mass times the distance from G to A. So this distance. So I assume that this is L. So this distance is going to be L divided by 2. So L divided by 2 square plus square. So if you simplify this, so you should get 4 by 12. I think you should get 1/6 ml square omega square. So this is T2. Okay, the final thing is U12. U12 is the work done due to external forces. So external forces there are 5 forces: H, V, capital M, small mg, and then K delta X. So the work done due to HA, VA is 0 because A does not move. So we only need to find the work due to the other 3 forces. So let's set that up one by one. M acts clockwise, and the angle turned is going to be, it turns from pi by 6, which is 30 degrees, to pi by 3. So it should be 60 minus 30 actually. It should be final minus initial. I think I got it wrong. 60 minus 30 degrees. So this should be final angle minus initial angle. Okay, and since the angle turned is clockwise and moment is clockwise, the sign on that is positive. Next is the work done due to mg. So mg times the displacement of the center of mass. How much does the center of mass get displaced? 30 degrees, it's here. This is, draw this again. This is 30 degrees. And then this is another 30 degrees, so total angle turn is 60 degrees. Okay, so what I need to do essentially is I need to find this distance. This is my delta y, right? Goes from here to here. I need to find the displacement, so times delta y. Okay, to find delta y, I just find this, which is L by 2 cosine of 30 degrees. And then I find this, which is L divided by 2 cosine of 60 degrees, right? Because this angle, total angle is 60, so when I resolve this in this direction, this distance is going to be L divided by 2 cosine 60. So the delta y is going to be the difference. This is going to be L divided by 2 cosine of 30 degrees minus L divided by 2 cosine of 60 degrees. Okay, and since mg is downwards and the displacement is downwards, force and displacement in the same direction, I have a positive on the force, on the work done. And the final part is due to the spring force, K delta X. plus the work done due to spring force is always, is it negative or positive? I think it's always negative, right? It's negative, always negative, k delta x square, where delta x square is the change in the length of the spring. Well, not true. It's the delta x is stretched length minus unstretched length. Okay, so the spring is unstretched when theta is 30 degrees and it's stretched when theta is 60 degrees. So I need to find the length. Draw blue. So this is going to be the length when it's unstretched. So let's call this S minus S0. So this is going to be S0 unstretched, and then in this position S0, and then when it goes down, this is the new length. So as long as I can find S1 and S0, I'm good. So S0 is simply, where is it attached? It's attached at L. So S1 is going to be L sine of 30 degrees, right? Because this distance is L, I need to find this one. So L sine of 30 is going to give me this, and then L times sine of 60 is going to be S1, give me S1. Okay, so this goes in right here. Okay, so given all that, let me try to put all this in the equation. So T1 is 0 plus U12 is all these things over here. I actually computed all of them, so I will just give you the answer I got. I got one sec. It's 19.81 equals 0.9375 omega square. If you solve for omega, you get 4.59 radians per second. So that is my final answer. So it's a little bit involved in terms of geometry and trigonometry, but it's very straightforward to solve this using work done. So I'll see you on Friday. I'm going to finish chapter 18 then, and then next week we're going to start with the next chapter. We just